This is our second and the last problem solving session on arithmetic, geometric and harmonic progressions. We resume this session with problem number 8. Now we have the following question. Let A, B and C be in an arithmetic progression and A square, B square, C square be in a geometric progression. If A is strictly less than B and B is strictly less than C, with A plus B plus C is equal to 3 by 2, then we shall find out the value of A. Since we know that A, B and C are in an arithmetic progression, we can take A as P minus R, B as P and C as P plus R for some P and R. Now we are given that A plus B plus C is equal to 3 by 2. So therefore we are getting P minus R plus P plus P plus R is equal to 3 by 2. So from here we are getting that P is equal to 1 by 2. Note that this is the value of B also. If we can now find out the value of R, then we know what is A, because A is nothing but P minus R. So half minus R. So we need to only find out now the value of R. In the question we are given that A square, B square and C square are in a geometric progression. So we have P minus R whole square, P square and P plus R whole square are in geometric progression. So we can write P minus R whole square into P plus R whole square is equal to P to the power 4. Therefore we get P square minus R square whole square is equal to P to the power 4. Hence P to the power 4 minus 2P square R square plus R to the power 4 is equal to P to the power 4. That means R square into R square minus 2P square is equal to 0. Note that A, B and C are distinct numbers. A is strictly less than B and B is strictly less than C. So here we can conclude that R cannot be equal to 0. Therefore we must have R square is equal to 2P square. That means we have R square is equal to 1 by 2. So R is equal to plus or minus 1 by square root of 2. So for A we are getting two possibilities, 1 by 2 plus 1 by square root of 2 or 1 by 2 minus 1 by square root of 2. Now recall that we are given A is strictly less than B and B is strictly less than C, and the value of b we know already is 1 by 2. Therefore, this choice of A is not possible, and hence A is 1 by 2 minus 1 by square root of 2. Therefore, here the third option is the correct answer. This is our question number 9. If the sum of the first n terms of an arithmetic progression is c into n square, then we shall find out the sum of the squares of those n terms. Note that the sum of first n minus 1 terms of this progression is c into n minus 1 square, because the sum of the first n terms is c into n square. Therefore, we know what is the nth term. The nth term is nothing but the sum of first n terms minus the sum of first n minus 1 terms. So, we have the nth term is c into n square minus c into n minus 1 square, which is c into 2n minus 1. So, we know what is the nth term of this arithmetic progression, that is c into 2n minus 1. Let us call nth term of this progression by AR. Our job is to find out sum over R running from 1 to up to n AR square. Now we know that this is nothing but, we can take c square out, and inside we have 2r minus 1 whole square. So, this is 4c square into sum running over r from 1 to up to n, r square minus 4c square into sum running over r from 1 to up to n, inside we have r, plus c square into sum over r running from 1 to up to n, inside we have 1. So, if we sum this up, we get 4c square into n plus 1 into 2n plus 1 divided by 6 minus 4c square into n plus 1 divided by 2 plus c square n. So, we take c square n divided by 3 common from this expression, and we get inside 2n plus 2 into 2n plus 1 minus 6n minus 6 plus 3. Simplifying that, we get c square n divided by 3 into 4n square plus 4n plus 2n plus 2 minus 6n minus 3, that is c square n divided by 3 into 4n square minus 1. So, now we know what is the sum of the squares of the first 10 terms of this arithmetic progression. The third option we can see is correct here. We consider the following question. For 1 less than or equal to I less than or equal to 101, let bi be strictly bigger than 1. Let log of b1, log of b2 up to log of b101 be in an arithmetic progression with the common difference log 2, and a1, a2 up to a101 be in an arithmetic progression so that a1 is equal to b1 and a51 is equal to b51. Now consider the sum of a1 to up to a51 to be s and the sum of b1 to up to b51 to be t. Then we shall find out among the 4 options given here which one is the correct answer. Since log of b1, log of b2 up to log of b101 is in an arithmetic progression with the common difference log 2, we can write log of b2 is equal to log of b1 plus log of 2, that is log of b2 is equal to log of 2b1. Now taking exponential on both sides, we get b2 is equal to 2b1. Next, let us look at log of b3. So log of b3 is equal to log of b2 plus log of 2. Now we know that log of b2 is equal to log of 2b1. So we are getting that log of b3 is equal to log of 2 square b1. Again we take exponential on both sides and we get b3 is equal to 2 square into b1. If we proceed in this way, we would obtain bi is equal to 2 to the power I minus 1 into b1 for all 2 less than or equal to I less than or equal to 101. So we are getting one form of bi for all I bigger than or equal to 2 in terms of b1. Next, let us write what is t. We know that t is b1 plus b2 plus b3 plus so on and so forth up to b51. So t is equal to b1 plus 2b1 plus 2 square b1 plus so on and so forth up to 2 to the power 50 into b1. Let us take b1 out and we get inside 1 plus 2 plus 2 square plus so on and so forth up to 2 to the power 50. Now note that this is a geometric series and this is equal to 2 to the power 51 minus 1. Therefore, we get T is equal to B1 into 2 to the power 51 minus 1. Next, let us try to write S in a simpler form. We know that S is equal to A1 plus A2 plus A3 plus so on and so forth up to A51. We can write A2 as A1 plus D, A3 as A1 plus 2D, and continuing this way we have the last term A1 plus 50D, where D is the common difference of the arithmetic progression A1, A2 up to A101. Now if we collect all the A1s together, we get 51 A1, and from the remaining terms we take D common and we get 1 plus 2 plus so on and so forth up to 50. Again we can see that this is an arithmetic progression and this is equal to 50 into 51 divided by 2. Let us now find out what is D. For that, we recall in the question we had A51 is equal to B51 and A1 is equal to B1. So A51 is equal to A1 plus 50D, as A51 is equal to B51 and A1 is equal to B1, we get B51 is equal to B1 plus 50D. So D is equal to B51 minus B1 divided by 50. Now we know that B51 is equal to 2 to the power 50 into B1. So we are getting D is equal to 2 to the power 50 minus 1 into B1 divided by 50. Now if we substitute this value of D here, and as A1 is equal to B1, we get S is equal to 51 B1 plus 2 to the power 50 minus 1 into 51 by 2 B1. We take 51 B1 out and inside we write 2 to the power 50 plus 1 divided by 2. To compare with T, we write this one as 51 B1 into 2 to the power 51 plus 2 divided by 4. We already got T is equal to B1 into 2 to the power 51 minus 1. Therefore, we can conclude that S is strictly bigger than T. So coming back to the question, option 3 and option 4 are not correct. Now we are going to see among A101 and B101 which one is bigger. We know that B101 is equal to 2 to the power 100 into B1 and A101 is equal to A1 plus 100D, and we have already got the value of D, which is 2 to the power 50 minus 1 divided by 50 into B1. Therefore, we have here A101 is equal to B1 plus, we are substituting B1 in place of A1, and this is here 2 to the power 51 minus 2 into B1. So basically we are getting 2 to the power 51 minus 1 into B1. So clearly B101 is strictly bigger than A101. Therefore, the second option is correct and the first option is incorrect. This is our 11th question. Let A1, A2, A3 and so on and so forth be an infinite harmonic progression with the first term being 5 and the 20th term being 25. We shall find out the least positive integer n for which an is negative. We write the nth term an as 1 by b plus n minus 1 into d for some b and d. Now note that a1 is equal to 1 by b. As a1 is given to be 5, therefore we get b is equal to 1 by 5. Also note that A20 is equal to 1 by b plus 19d. Therefore, b plus 19d is equal to 1 by A20, which is equal to 1 by 25, and we know b is equal to 1 by 5. Therefore, d is equal to minus 4 by 25 into 19. Now our job is to find out the least positive integer n so that an is strictly less than 0. As an is 1 by b plus n minus 1 into d, we shall find out the least positive integer n for which b plus n minus 1 into d is strictly less than 0. We know b is equal to 1 by 5 and we also know the value of d. So we use this inequality to find out the range of n for which an is negative. Now substituting the value of b and d, here we get 1 by 5 plus n minus 1 into minus 4 by 25 into 19 is strictly less than 0. This implies 1 plus n minus 1 into minus 4 divided by 5 into 19 is strictly less than 0. This implies n minus 1 shall be strictly bigger than 5 into 19 divided by 4. That is, n shall be strictly bigger than 5 into 19 divided by 4 plus 1, and this is equal to 99 divided by 4. So therefore n has to be bigger than or equal to 25 so that an is strictly less than 0. Therefore 25 is the least positive integer for which an is negative. Hence we get option 4 is correct. In this question we have 4 distinct numbers a1, a2, a3 and a4 which are in a geometric progression. We have b1 is equal to a1 and bi is equal to bi minus 1 plus ai for all I is equal to 2, 3 and 4. Then we have two statements. The first statement is the numbers b1, b2, b3 and b4 are neither in arithmetic progression nor in geometric progression. And second statement is the numbers b1, b2, b3 and b4 are in harmonic progression. We have to check whether statement 1 and statement 2 are correct or not, and in case both the statements are true, we have to check whether statement 2 is a correct justification of statement 1 or not. We have b1 is equal to a1 and b2 is equal to b1 plus a2. As b1 is equal to a1, we get b2 is equal to a1 plus a2. Now b3 is equal to b2 plus a3. So b3 is equal to a1 plus a2 plus a3, and b4 is equal to b3 plus a4. So b4 is equal to a1 plus a2 plus a3 plus a4. Note that from here we get b2 minus b1 is equal to a2 and b3 minus b2 is equal to a3. We are given that ai's are all distinct, so a2 is not equal to a3. That means b2 minus b1 is not equal to b3 minus b2. So we have 2b2 is not equal to b1 plus b3. This implies b1, b2, b3 are not in arithmetic progression. So b1, b2, b3 and b4 are not in arithmetic progression. Next we check whether B1, B2, B3 and B4 are in geometric progression or not. For that, let us write AI as A1 into R to the power I minus 1 for all I is equal to 2, 3 and 4, as we are given that A1, A2, A3 and A4 are in a geometric progression. Here this R is the common ratio of the geometric progression A1, A2, A3, A4. Let us make a small note here that A1 is not equal to 0 and R is not equal to 0, because if A1 is equal to 0 or R is equal to 0, then it contradicts the fact that AIs are all distinct. Using this, we obtain B2 is equal to A1 plus A1R. So this is nothing but A1 into 1 plus R. B3 is equal to A1 plus A1R plus A1 R square, which is same as A1 into 1 plus R square, and B4 is equal to A1 plus A1R plus A1R square plus A1R cube. That is, B4 is equal to A1 into 1 plus R square plus R cube. Now, if B1, B2, B3 and B4 are in a geometric progression, then we must have B1 into B3 is equal to B2 square. Let me write it here. If B1, B2, B3 are in a geometric progression, so we shall have A1 into 1 plus R square is equal to A1 square into 1 plus R whole square. Now, as A1 is non-zero, we can cancel A1 from both sides and we get 1 plus R square has to be equal to 1 plus R whole square, that is 1 plus 2R plus R square. Recall that we already got R is not equal to 0. We can easily note that for R not equal to 0, this equality does not hold. So, in this case, we do not get B1 into B3 is equal to B2 square. That is, we have B1 into B3 is not equal to B2 square. So, B1, B2, B3 and B4 are not in geometric progression. So here our statement 1 is true. So we can immediately strike off option 1. Next we check whether statement 2 is correct or not. For that we have to check whether B1, B2, B3 and B4 are in harmonic progression or not. If B1, B2, B3 and B4 are in harmonic progression, then we must have 1 by B1 plus 1 by B3 is equal to 2 by B2. That is, we shall have 1 by A1 plus 1 by A1 into 1 plus R square is equal to 2 by A1 into 1 plus R. That is, we shall have 1 plus R square plus 1 divided by 1 plus R square is equal to 2 by 1 plus R. That is 1 plus R into 2 plus R square shall be equal to 2 into 1 plus R square. Simplifying this, we get 2 plus R square plus 2R plus R square plus R cube shall be equal to 2 plus 2R plus 2R square. That is, we shall have R into 1 plus R square is equal to 0. That is, we shall have R is equal to 0 or R is equal to plus minus I. Now recall that we have already made this remark that R is not equal to 0, as A1, A2, A3 and A4 all of them are distinct, and if R is equal to plus minus I, then note that B4 is equal to A1 into 1 plus R square plus R cube is equal to 0. Therefore, B1, B2, B3 and B4 cannot be in harmonic progression. So we see that statement 2 is false, and already we have seen that statement 1 is true. So option 4 is the only correct answer. This solves our question number 12. Here is the question number 13. Let A1, A2 up to A100 be in an arithmetic progression with A1 being 3, and let us call sum over I running from 1 to up to P AI as SP for all 1 less than or equal to P less than or equal to 100. For any integer n with 1 less than or equal to n less than or equal to 20, we take m to be 5n. Then if Sm by Sn does not depend on n, we shall find out the value of A2. First note that to find out the value of A2, it is enough to find out the value of the common difference of this arithmetic progression. Let us call D to be the common difference of this arithmetic progression. Now A2 is nothing but A1 plus D. So as we know what is A1, if we can find out what is D, we will know what is A2. We have SP is equal to sum over I running from 1 to up to P AI. So this is equal to P into A1 plus 1 plus 2 plus so on and so forth up to P minus 1 into D. We know that A1 is equal to 3. So we substitute it here. So SP is equal to 3P plus P into P minus 1 divided by 2 into D. Let us take P by 2 common, then we get inside 6 plus P minus 1 into D. Now we write what is Sm by Sn, where m is equal to 5n. So Sm by Sn is equal to S5n by Sn, and this is equal to 5n by 2 into 6 plus 5n minus 1 into D divided by n by 2 into 6 plus n minus 1 into D. Cancelling n by 2 from the denominator and the numerator, we get 30 plus 25n minus 5 into D divided by 6 plus n minus 1 into D. In the question we are told that Sm by Sn does not depend on n. That assures that Sm by Sn is a constant. Let us call that constant as C. So we have 30 plus 25n minus 5 into D is equal to C into 6 plus n minus 1 into D. To emphasize, we have Sm by Sn is a constant which we have called here by C because Even if n changes, the ratio Sm by Sn does not change. Now from this equation we get 30 plus 25 Nd minus 5D is equal to 6C plus Cnd minus Cd. So 25 minus C into Nd is equal to 6C minus Cd minus 30 plus 5D. Therefore, if 25 minus C into D is non-zero, then we get a definite value of n from this equation. But this equation is true for all n bigger than or equal to 1 and less than or equal to 20. So we must have 25 minus C into D is equal to 0. From here we get either D is 0 or C is equal to 25. Now if D is equal to 0, then we get A2 is equal to A1 plus 0. So A2 is equal to 3. And if C is equal to 25, then 30 plus 25 Nd minus 5D divided by 6 plus Nd minus D is equal to 25. Therefore, 30 plus 25 Nd minus 5D is equal to 150 plus 25 Nd minus 25 D. Therefore, 20D is equal to 150 minus 30, which is equal to 120. So from here we obtain D is equal to 6. So in this case we get A2 is equal to A1 plus 6. So A2 is equal to 9. Hence A2 has two possible values, namely 3 and 9. This solves our question number 13. This is our 14th question. Let A, B and C be three positive integers such that B by A is an integer. If A, B and C are in a geometric progression and the arithmetic mean of A, B and C is B plus 2, then we shall find out the value of A square plus A minus 14 divided by A plus 1. Since A, B and C are in a geometric progression, we write A as B by R and C as B into R, where R is the common ratio. We are given that B by A is an integer. In fact, we know that B by A is a positive integer as B and A, both of them are positive. Note that From here we obtain R is equal to B by A. Therefore, we can conclude that the common ratio R is a positive integer. We denote the set of positive integers by Z in the subscript strictly bigger than 0. We know the arithmetic mean of A, B and C is B plus 2. Therefore, A plus B plus C divided by 3 is equal to B plus 2. That means A minus 2B plus C is equal to 6. We substitute A is equal to B by R and C is equal to BR in this equation. We then get B by R minus 2B plus BR is equal to 6. That is B minus 2BR plus BR square is equal to 6R. We can write it as R square minus 2R plus 1 into B is equal to 6R. So, B by R into R minus 1 whole square is equal to 6. We could divide by R because we know R is non-zero. Now, recall that B by R is equal to A. Therefore, we have A into R minus 1 whole square is equal to 6. We also know that A and R, both of them are positive integers. Note that the only possible positive integer solution of this equation is R is equal to 2 and A is equal to 6. So we substitute A is equal to 6 in this expression. A square plus A minus 14 divided by A plus 1, and we get this is 36 plus 6 minus 14 divided by 7, that is 28 by 7. So we get the value of this expression is 4. So this solves our question number 14. Let us now look at the following question. Suppose that all the terms of an arithmetic progression are positive integers. If the ratio of the sum of the first 7 terms to the sum of the first 11 terms is 6:11 and the 7th term of the progression lies between 130 and 140, then what is the common difference of this arithmetic progression? Let us denote the common difference of this arithmetic progression by D. And Nth term of this progression by AR. Therefore, we have AR is equal to A1 plus R minus 1 into D for all R bigger than or equal to 1. We are given that AR belongs to the set Z strictly bigger than 0. That means AR is a positive integer for all R bigger than or equal to 1. Therefore, we can conclude that D is also a positive integer because D is nothing but A1 plus D minus A1, and we know this is a positive integer and also this is a positive integer. Alright, in the question we are also given that sum over I running from 1 to up to 7, AI divided by sum over I running from 1 to up to 11, AI is equal to 6 by 11. Now note that sum over I running from 1 to up to 7, AI is equal to 7A1 plus 1 plus 2 plus so on and so forth up to 6 into D. Note that this is equal to 6 into 7 divided by 2. Therefore, this sum turns out to be 7 into A1 plus 3D. Next, we consider the sum over I running from 1 to up to 11, AI. This is equal to 11A1 plus 1 plus 2 plus so on and so forth up to 10 into D. So this is 11A1 plus 10 into 11 divided by 2 into D. So this sum turns out to be 11 into A1 plus 5D. Therefore, from this equation we get 7 into A1 plus 3D divided by 11 into A1 plus 5D is equal to 6 by 11. That means 7A1 plus 21D is equal to 6A1 plus 30D. That is A1 is equal to 9D. We are also given that 130 is strictly less than A7 and A7 is strictly less than 140. Now A7 is A1 plus 6D, and as A1 is equal to 9D, we get A7 is equal to 15D. So therefore we have 130 divided by 15 is strictly less than D, and D is strictly less than 140 divided by 15. So we get this inequality. 26 divided by 3 is strictly less than D, and D is strictly less than 28 divided by 3, we can write it like this: 9 minus 1 by 3 is strictly less than D, and D is strictly less than 9 plus 1 by 3. As we know, D is an integer, we get D is equal to 9. So, the common difference of this arithmetic progression is 9. With this, we conclude our problem solving session on arithmetic, geometric and harmonic progressions.